A Boeing 767 is climbing out over the dense jungles of northern Thailand. The pilots are settling into their seats for the long flight ahead when suddenly a warning related to the aircraft's thrust reverser system appears. This is the start of a terrifying chain of events that the aircraft manufacturer didn't even think was possible. Stay tuned. On the 26th of May 1991, a crew from Lauda Air was getting ready for a two-leg flight, bringing them from Kai Tak Airport in Hong Kong towards Bangkok in Thailand and then finally towards their home base in Vienna, Austria. This was part of a 3 times weekly service that Lauda Air was doing between Bangkok and Vienna, and the aircraft that was being flown was a Boeing 767-300 that had been purchased new to Lauda Air only about 2.5 years earlier in October 1989. This aircraft was a long-range version of the Boeing 767 and it was equipped with 2 Pratt & Whitney 4060 high-bypass turbofan engines. These engines were state-of-the-art, they were very, very efficient, but the way that they were constructed is going to have a major impact on what's about to happen, so we're going to have to become a little bit technical now. A high-bypass turbofan engine is basically an engine where the majority of the thrust that is pushing the aircraft forward is produced by the big fan in front of the engine, rather than the air that passes through the core and the burn chambers. In the case of the Pratt & Whitney 4060 engines, the bypass ratio was about 5:1, meaning that there was 5 times as much volume of air that passed the bypass duct of the engine than what passed through the core of the engine. This high bypass ratio meant a lot better fuel economy and also much lower noise on these new engines, because it turns out that using the fan to move a larger volume of air at a slower speed is much more efficient than trying to accelerate a smaller volume of air into higher speed. This is, by the way, why all modern engines seems to be getting bigger and bigger, but that's a slightly different story. Another consequence of this shift in design was that the engine's thrust reversers could now be constructed differently. On older type of jet engines, the reverse thrust was constructed by 2 buckets being extended and then deployed into the core airflow, basically redirecting the whole core airflow into a forward angle. But with these new high bypass engines, it was found that it was much more efficient to use 2 translating sleeves that would move back, and they would then extend blocker doors into the bypass duct. That would redirect the bypass flow forward through some fixed cascade vanes, and that would create the reverse thrust. However, another consequence of this was that the reverse thrust was now being created in a slightly different place. While in the old engines, the reverse thrust was being created at the very back of the engines, now the reverse thrust was being created much further ahead, and that is going to have an impact on what's about to happen. But why is reverse thrust so important? Well, as the aircraft kept becoming bigger and heavier and started to be able to fly during all sorts of different types of weather, it became very apparent for the industry that the aircraft needed more than one way to decelerate after landing or doing a rejected takeoff. The thrust reversers created a different type of braking than what the wheel brakes would, and it turned out that especially during operations on wet or slippery runways, the reversers were extremely important. And even if they operated the aircraft on dry runways, the reversers helped to take some energy away from the brakes, which meant that the temperature of the brake discs could be lowered substantially. Now, the reversers on commercial aircraft were only certified to operate on the ground, and because of that, the aircraft manufacturers had built in several redundant systems to make sure that they couldn't be deployed once the aircraft was airborne. On the Boeing 767, this was accomplished by a safety mechanism that connected the weight on wheel switches of the aircraft. Those are switches that can feel if the aircraft is on the ground or if it's airborne, was connected to 2 electrically activated hydraulic valves that both independently could make sure that the thrust reversers remained closed whilst the aircraft was airborne. The first valve was called a hydraulic isolation valve, the HIV, and it received signals from the weight on wheel switches, and when the weight on wheel switches indicated that the aircraft was airborne, the hydraulic isolation valve just cut access from hydraulic fluid into the thrust reverser mechanism. And this was true any time that the aircraft was airborne, except when a system called the restow circuit was active, but we'll get to that later on. If for whatever reason the hydraulic isolation valve would malfunction during flight and allow hydraulic fluid into the thrust reversers, that would send a warning to the pilot called reverser isolation, notifying them that this was going on. Remember that. Now, following the hydraulic isolation valve was a second valve called the directional control valve, the DCV. The directional control valve then directed hydraulic fluid to either deploy or close the thrust reversers, and the directional control valve was defaulted into the closed position. So together, these two valves were built in a way that should ensure redundancy to keep the thrust reversers closed whenever the aircraft was airborne. On top of this, the engines were constructed to automatically reduce the thrust on the engine back to idle in case it felt that any of the thrust reverser sleeves was starting to move. But of course, no system is completely foolproof, and that had been proven by a couple of uncommanded thrust reverser deployment in flight on some other aircraft types, including the DC-8, the DC-10, the Boeing 707 and the Boeing 747. And because that had happened, the FAA had mandated Boeing to, before certification, prove either through flight tests or in-flight modeling that the aircraft would be able to be handled properly in case a thrust reverser would deploy in flight. Those tests and models were built based on a couple of assumptions, namely that this thrust reverser deployment would happen to an aircraft which was at a relatively low both altitude and airspeed. And the reason it was made like that was because that was seen as the most critical scenario. Because if the airspeed is low, it means that the effect of the flight control surfaces would also be lower. That would be detrimental when it came to handling the effects of the asymmetric thrusts that the thrust reverser deployment would cause, and also the loss of lift on the wing that had happened. The test and models also assumed that the engine would be back at idle thrust before the thrust reverser deployment event would happen. And that was because of the way that the engines had been designed, that the thrust reverser sleeves shouldn't be able to start moving unless the engines were first back at idle. With all of these assumptions met, the model showed that the wing that was associated with the deployed thrust reverser would only lose about 10% of its lift due to the air that was now being forced forward by the thrust reverser, disrupting the airflow at the leading edge of the wing. This would cause a moderate roll, and together with a yaw that was induced by the asymmetric thrust, this would only lead to moderate problems with controlling the aircraft, something that was well within the capabilities of a trained pilot. On the 26th of May, the day started just like any other day for the crew. The pilots met up in the crew room in Hong Kong and started going through the flight plan, the NOTAMs, the weather, and all of the other briefing material. And once they were done with that, they talked to the cabin crew, and then together they went out to the aircraft. When they came into the aircraft, the captain went through the technical log, and the technical status of the aircraft was perfectly fine. It was perfectly airworthy. Now, if the captain would have looked back through the technical history of the aircraft, he would have noticed that there had been some work carried out on this aircraft by the technical department. Specifically, there had been several instances of fault messages being sent from the left-hand thrust reverser. These were minor fault messages, but the maintenance department in Lauda had been troubleshooting this on and off for the last 6 months or so. They had followed the fault isolation manual that Boeing had provided to them, and that had led them to replace some of the components inside of the thrust reverser. That would work for a little while, but after a few flights, similar fault messages would start reappearing again. Now, because these faults were indicated as minor and not critical, the dispatch deviation procedure guide actually allowed the aircraft to be dispatched and to fly with these fault codes for up to a maximum of 500 hours before it had to be rectified. And every time that they did something that rectified the fault, these 500 hours would be reset. So this was why the aircraft had been flying with these reoccurring fault messages for the last 6 months. The technical engineering department was not happy with this though, so they had started to inspect all of the electrical wire bundles that was going out to the left-hand thrust reverser to see if maybe there was something in there that was causing these fault messages to appear. But since this was not a mandatory inspection and not part of the normal maintenance schedule, they did this on and off, and meanwhile the aircraft kept flying. So even if the captain would have gone back through the tech log and seen that this maintenance work had been carried out and was going on, it is unlikely that he would have reacted to it, because according to the tech log it was fully airworthy with no limitations whatsoever. The captain of the flight was a 48-year-old American citizen with about 11,750 hours of total flight experience. He was assisted by a 41-year-old first officer with just over 6,500 hours, and together with them were 8 cabin crew members on this flight. On the first flight from Hong Kong over towards Bangkok, the first officer was pilot flying. They taxied out in Kai Tak, took off completely normally, and proceeded to fly over to Bangkok without any indication of any type of problems. They landed on time according to schedule, taxied into their stand where they proceeded to do a normal turnaround, uploading more fuel, passengers and cargo, getting ready for their flight back towards Vienna. But before we get into that flight, which is going to turn out to be the accident flight, I just want to share this exclusive offer to you from my sponsor. This video is sponsored by NordVPN. Come a little bit closer. Closer. I'm going to tell you a secret. I can be anywhere I want within seconds. Canada, the US, Sweden, Japan, you just name it. A platform is not available in your country? Well then, with NordVPN you can just change your virtual location. You can choose between more than 5,400 servers in 60 countries with just one click. No limits, no borders and no censorships, and you can even find specific discounts in other regions. Unblock your favorite games or geo-restricted servers, and NordVPN will always encrypt all of your data, so your internet service provider can't reduce your streaming speed. I have always peace of mind because I know I'm safe when I'm using NordVPN, and now users can route their data to 2 different VPN servers at once. And they've added a new feature called the threat protection, which makes browsing both smoother and safer even if you're not connected to a VPN server. So get your exclusive deal and a huge discount off the normal price using the link in the description below, which is nordvpn.com/pilot. And you're not risking anything because NordVPN has a 30-day money-back guarantee. Now back to the video. On the second flight of the day, the captain was going to be pilot flying. The pre-flight setup, the walk around and all the general preparation was completely normal, and at time 16:02, that's 23:02 local time, the aircraft received its pushback clearance and pushed back from the gate to start to taxi out for departure on runway 21 left in Bangkok. On board the aircraft was 213 passengers, 8 cabin crew members and 2 pilots. And at time 23:15, Lauda Air Flight 004 started rolling down runway 21 left for takeoff. The takeoff was completely normal. They started climbing initially to 7,000 feet and turned towards the northwest. The weather in the area was quite good. It was a little bit cloudy, temperature of 26 degrees with some light winds and some forecast of thunderstorms in the general area, but nothing indicated that any thunderstorms were close to the flight path of Flight 004. After takeoff, the first officer contacted the Bangkok departures ATC frequency. The flight was then cleared to continue to climb to 11,000 feet and turn towards a waypoint called Limbo. This was read back by the first officer, who was then told to contact the next departure controller. The new controller told the flight to continue climb to flight level 310, that's 31,000 feet, and continue on the flight plan route. The flaps were retracted as per normal procedures, and once the flaps were up, the first officer completed the after takeoff checklist, and he then started to complete the flight plan, to fill in the actual departure time, to calculate the times over each waypoint and the fuel they could expect at each waypoint. And then once he was done with this, he passed on those figures on to the ground controller, the operations controller in Bangkok for Lauda Air, so that they could follow the progress of the flight. About 4 minutes and 45 seconds into the flight, the first officer suddenly exclaims, "Shit, that keeps coming on," referring to a left reverser isolation warning. Now, the way he says it indicates that this warning must have been coming on and going out a couple of times before he actually says something about it. Now, do you remember what the reverser isolation warning actually means? Exactly. This means that the hydraulic isolation valve that keeps the hydraulic fluid away from the thrust reverser mechanism is now open in flight. The captain acknowledges this and tells the first officer to please take out the quick reference handbook non-normal checklist for the specific failure. The first officer does so, he finds the checklist, but when he starts reading the checklist it doesn't really have any action items. It gives a little bit of information about the fault, and then it says that additional failures might cause in-flight thrust reverser deployment. It also says that the pilots can expect normal operation of the thrust reverser after landing. This likely reassures the pilots, because anytime that a QRA checklist doesn't have any action items in it and doesn't tell the pilots to land at the closest suitable airport, it basically means that the failure is not that critical. And the fact that the checklist just casually refers to any additional failures might cause an in-flight deployment of the thrust reverser, that just says that because, remember, there's still the directional control valve that is supposed to keep the thrust reversers closed. And the in-flight testing that had been done prior to the certification of the aircraft has shown that even if the thrust reversers does deploy, it should be okay, easily handled by the pilots. Now, there is an additional checklist for an actual in-flight deployment of the thrust reverser, and that checklist basically just tells the pilots to shut the associated engine down to minimize the effect of the reverser. The pilots now keep discussing this indication as they're climbing away further, and the first officer suggests that maybe they should contact the handling frequency in Bangkok to tell the engineering department that they have this problem and see if they have any guidance for them. The captain says that that's a great idea, contact them, but tell them that it's likely moisture or something, because the indication keeps coming on and off all the time. Now, I understand why the captain thought this, because a lot of warnings in an aircraft is triggered by microswitches. These microswitches are monitoring the position of certain components, and sometimes moisture or contamination can get into these microswitches and make them give faulty warnings. Actual faults tends to be more permanent in nature, so when you have a small warning like this going on and off, blinking like that, given the amount of information that the captain knows at this point, I would probably have thought the same. In any case, the aircraft continues to climb up towards 31,000 feet that they've been cleared, and a few seconds later the first officer remarks to the captain that it looks like he needs a little bit of left trim. What the first officer likely means is that he can see that the steering wheel is slightly displaced towards the left. This can happen when there is some unexpected drag on one side of the aircraft, in this case on the right-hand side, that causes a little bit of a yaw, and the autopilot responds to this by putting aileron in against that side to make sure that the aircraft keeps flying straight ahead. But obviously flying with ailerons like that is not the most economical thing to do. So what we do is that we have a little rudder on the back side of the main rudder that you can displace in order to counteract that yaw. That will then center the steering wheel, and the aircraft will continue to fly straight ahead, but in a more clean configuration. Now, this remark is unlikely to have anything to do with what's about to happen next. About 4.5 minutes after the first officer made the comment about the trim, this is 15 minutes and 1 second into the flight, the first officer suddenly exclaims, "Oh, the thrust reverser is deployed." At this point, the aircraft is at an altitude of 24,700 feet, climbing with a speed of Mach 0.78 and with the engines producing full climb thrusts. The next thing that can be heard on the voice recorder is sound similar to the aircraft shuddering and a metallic snap. The aircraft now enters into a rapid roll to the left, accompanied by a violent pitch down, and within seconds several warnings can be heard on the cockpit voice recorder, including the altitude alert and several master caution warnings. A second metallic snap can then be heard, followed by the captain exclaiming, "Jesus Christ!" followed 12 seconds later by the captain saying, "Here, wait a moment," and then 5 seconds after that, "Damn it!" Evidence indicates that it took the pilots approximately 10 seconds to shut the left engine down, but at that point it was already too late. As this is all happening, you can hear on the cockpit voice recorder how the background noise is steadily increasing, indicating a higher and higher indicated airspeed. This is then later accompanied by a continuous overspeed warning. But why is this happening? The aircraft is supposed to be controllable even if one of the thrust reversers are deployed. Well, it turns out that when the modeling was done, it was based both on a much lower airspeed, about 200 knots, and this aircraft is actually making Mach 0.78, and it also assumed that the engine would have been spooled back to idle before the reverse thrust was activated. In this case, whatever failure that caused the thrust reverser sleeves to start moving backward did so while the engines were still producing climb thrust. And remember how we were talking about these new reversers? They produced thrust a little bit further forward on the engines. Well, this meant that as these thrust reverser sleeves were now moving backwards, they produced an enormous plume of reverse air that came out just in front of the leading edges of the wings, likely reducing the lift available on that wing with as much as 25%, not the 10% that the models had shown. This sudden and violent onset of reverse thrust on the left-hand side initiated a 28 degrees per second roll towards the left together with a violent yaw due to the asymmetric thrust situation. The pilots would have had to immediately initiate full right rudder and full right aileron to try to counteract this, together with reducing the thrust on the operating right engine to minimize the thrust asymmetry. But here, the pilots would have faced their next hurdle, which is that as this descent initiated, they were already at a speed of Mach 0.78. And as the speed now continued to increase, as we could hear from the cockpit voice recorder and the overspeed warning, it meant that the pressures and the stresses on the aircraft would have built up enormously. And that would have meant that the pilots would have had to be very, very careful in order to not overstress the aircraft structure as they tried to both maneuver out of the situation and pull the aircraft out of the dive. Simultaneously, as the aircraft is now accelerating and getting closer to the speed of sound, the effect of the flight controls will start to become less effective due to elasticity and aerodynamic Mach effects. And if you put that together with the fact that they're still suffering from asymmetric thrust from the now deployed thrust reverser, it together means that this situation became completely uncontrollable within seconds after the thrust reverser deployed. What now follows is a terrifying example of what happens to an aircraft when it exceeds its maximum both speed and maneuvering loads. We don't know exactly how high the speed became in the end, but we do know from the EEC memory on the left-hand side that it recorded Mach 0.99 as its highest value, and that was likely the highest value that it could record. In reality, it is a possibility that this aircraft exceeded Mach 1 during its descent down towards the ground. The first parts that separated the aircraft were sections of the rudder and the left elevator, probably due to buffeting overload. This was then followed by a large section of the right horizontal stabilizer that was ripped off the aircraft as the pilots tried to pull it out of the dive. The fact that most of the right stabilizer was now gone and not on the left-hand side started creating asymmetrical forces on the back of the aircraft, basically acting like a giant hand turning a corkscrew. This damaged both the skin and the connecting structure in the tail, leading to the separation of what was left of the horizontal stabilizer and the tail fin. Without the stabilizing downforce from the stabilizer, the aircraft now turned into an almost vertical dive, increasing the speed even further. This led to the stresses on the wings just becoming too great, which meant that the wings now broke off, and as that happened, that ignited the fuel inside of the fuel tanks, leading to an enormous fireball that could be seen by eyewitnesses on the ground. On the cockpit voice recorder, the complete breakup of the aircraft could be heard as a series of bangs and metallic snaps about 26 seconds after the initial indication of the thrust reverser deployment. This was calculated to have happened at approximately 4,000 feet, and about 3 seconds later the aircraft impacted the ground. There were no survivors of this accident, making this the first deadly accident of a Boeing 767 and the worst aviation disaster in Thailand to this day. Unfortunately, the post-impact fire also completely destroyed the flight data recorder, making it impossible to find out for sure what parts of the system caused the in-flight thrust reverser deployment. The crash site was also looted before the investigation team could get there, and one of the things that the looters took with them was the hydraulic directional control valve from the left-hand engine, which was a crucial piece of evidence. The valve was eventually returned to the investigation team about 9 months after the accident, but there were indications that it had been tampered with when it was returned. So now the investigation team had to try to figure out what had happened, and they didn't have the flight data recorder in order to help them. So they started looking back through any kind of similar fault that had happened on the Boeing 767 fleet, and they quickly found that there were some wiring issues leading up to the thrust reverser system that could potentially leave the hydraulic isolation valve to open up in flight, causing the kind of indications that the pilots had reported during this flight. Now, if that fault existed and it was combined with another short circuit within the electrical system, that could potentially lead to the directional control valve activating a thrust reverser deployment in flight. The investigation team also found that if the hydraulic isolation valve was open for whatever reason and there was some contamination or blockage inside of the directional control valve, that blockage could also lead to an activation of the thrust reverser. As soon as the investigation revealed this, Boeing issued a technical service bulletin that mandated several upgrades to the Boeing 767s that were fitted with Pratt & Whitney 4000 model engines. The first thing that was mandated was that all thrust reversers was deactivated until the upgrades could be implemented, and the upgrades included things like a dedicated restore circuit, much better and individual electrical wiring, and a few other things as well that after the upgrade made a thrust reverser deployment in flight virtually impossible. But there was still the issue with why this aircraft couldn't be controlled. It had been certified, the pilots should have been able to handle it. Lauda Air spent a lot of resources on this, and Niki Lauda himself was deeply involved in the investigation work. Among other things, they tried to replicate the flight in a flight simulator, and when they did that, it showed that this event should have been controllable. But it turned out that the simulators just did not have the correct performance parameters to accurately simulate the handling characteristics in this incident. And when Boeing heard about this, they initiated wind tunnel testing with a model very similar to a Boeing 767 in low-speed wind tunnels, and then they extrapolated to see what would happen in higher speed scenarios. And when they got the data from that, they put that into one of their own simulators, and they had the Boeing chief technical pilot actually try to fly it. And he very quickly realized that unless the pilots did everything right within 4 to a maximum of 6 seconds after an in-flight deployment with this kind of situation, it would have been impossible for the pilots to recover. So Boeing basically conceded that an untrained flight crew that was given this type of situation would not be expected to be able to handle it. This accident really opened the eyes of the industry into the possibilities and the risks associated with an in-flight thrust reverser deployment event. It spurred a lot of innovation into system design improvements and redundancies to keep this thing from happening. The investigation recommended revisions in how the FAA certified aircraft with thrust reversers to make sure that they couldn't deploy in flight, and also improvements on how the cockpit voice recorder and the flight data recorder could be further insulated and kept away from damage in case of a post-accident fire. Now, if you want to learn more about the black boxes and whether or not we will eventually be streaming that data up into the cloud rather than having it stuck inside of the black boxes, well, then check out this video that I just did on my new channel, Mentour Now, which I hope you have subscribed to. If you want to continue to binge watch incidents and accidents, then check out this playlist up here. And if you want to support the work that I do, then consider becoming part of my brilliant Patreon crew or get yourself some merch. Have an absolutely fantastic day, and I'll see you next time. Bye-bye.